So let's welcome Stanislaw Kaushanski, who works for MINRES as a senior developer, and he's going to talk about automated cross-level verification flow of a highly configurable RISC-V core family with custom instructions.
Thank you. Hello, my name is Stanislaw Kaushanski, and I'm senior developer at MINRES Technologies. And today I would like to share our experience in verification of highly configurable RISC-V cores. First, a few words about MINRES Technologies. The company was established in 2012, and since 2017 we are a member of RISC-V International. And since 2019, we are developing a family of RISC-V cores. So at MINRES, we are deeply inspired by the concept of software-defined hardware development, which holds two significant meanings for us. Firstly, we extensively use software techniques and methodologies in our hardware development process. And secondly, we think that the hardware design process should be closely aligned with software requirements. And this is why we put a high priority on the flexibility and extendability of our cores. So the TGC cores are designed to offer high flexibility, scalability, and extendability. And to simplify the core selection process, we defined 5 standard configurations, which serve as a starting point, building a foundation, for definition of the final feature set. So the TGC family allows a combination of different features and options, like different bus interfaces, interrupt controllers, processor caches, of course custom instructions, and also safety and security features. So building such a flexible core family is quite a big task for a small company like ours, but ensuring the quality of these cores is even a bigger challenge. So the question was, how can we verify all combinations, all these cores with custom instructions in the most efficient way? And we found an answer in reusability and high level of automation. So our verification process starts with a description of the architectural state of the core, which will be used as a single source of truth. So for this purpose, we use CoreDSL, a domain-specific language, to model processor cores at the level of their instruction set architecture. And from this CoreDSL description, we automatically generate several components. For example, the full-blown instruction set simulator, but also configuration files for test bench elements, properties for formal verification, artifacts for toolchain compatibility to enable the usage of custom instructions by the target firmware. And last but not least, with assistance of HLS tools, we create hardware for custom instructions and seamlessly integrate this hardware into the existing microarchitecture of the TGC core. So CoreDSL The main advantage of CoreDSL is its simplicity. So the idea behind CoreDSL is everybody should be able to create a custom instruction for the RISC-V core. So you don't have to be a hardware developer to be able to create it. And here is a short example of CoreDSL description. So on the top level, you define your core, and then there are several sections. So for example, the first section describes an architectural state of the core, and the second section shows a definition of an instruction. So as you can see, it takes only few lines to define a simple instruction. Of course, there are several optional features which can be added, but still the idea is the description remains short and easy to understand. So the generated components from the CoreDSL description will be seamlessly integrated into the UVM cross-level test bench. And for the setup of this test bench, we choose to use the UVM-SystemC library because it brings the strengths of both the UVM methodology and SystemC, and it significantly simplifies the integration of the ISS into the UVM environment, because both are actually implemented in C++. So in a nutshell, the test bench uses ISS as a reference model, and instruction generator creates an instruction which will be fetched by both ISS and RTL DUT. The external behavior of the ISS and also its internal state will be observed and sent to the scoreboard, where it will be compared to the results from the RTL. And so this test bench can also operate in two modes. So the first mode, in random mode, we just generate an endless stream of random instructions. And in additionally, the test bench allows to load and execute ELF files. So we can test specific scenarios, or we can also execute other test suites like Google RISC-V DV tests or RISC-V architectural compliance tests. But in this presentation, we are concentrating on the random approach. So the test starts in a virtual sequencer, which basically consists of the instruction generator and the ISS reference model. The instruction generator is a generic module, but it has access to the information generated from this CoreDSL description. So it can randomly pick an instruction from the generated list, and yeah, it also tracks all executed instructions and dynamically adjusts the instruction frequency to optimize coverage. So this coverage aging mechanism allows to speed up a good coverage achievement. And the functional coverage monitor also relies on the information provided by the CoreDSL description. It needs also the information about all the implemented instructions in this particular DUT to be able to accurately track and report coverage metrics. So the data produced in this virtual sequencer will be transferred to the IBUS and DBUS agents, and these agents are connected to the DUT over the virtual interface. The virtual interface enables communication between the test bench and the DUT without being bound to a specific implementation. this flexibility allows us to easily exchange the DUTs, so different cores, and even more, we can exchange the simulation engines. For example, we use pin-level adapter to connect the test bench to the very latest RTL design, but we can also use UVM Connect library and run the same simulation with the commercial system Verilog simulator. Or we can even set up a hybrid simulation with Raven. Raven is a MINRES tool which allows us to run the DUT on FPGA while the test bench elements are running on hosts. And after each clock cycle, the core updates the information on the trace interface, which provides an insight into the core internal state. And this information will be captured by the trace monitor and forwarded to the scoreboard. And if all checks are passed successfully in the scoreboard, then this instruction will be forwarded to the functional coverage monitor. The functional coverage monitor collects and reports coverage information using cover points and cover groups. So cover point describes how the coverage should be collected for a particular instruction type, and cover groups summarize the information from different cover points. So, in conclusion, we have a highly effective verification solution. And because with this approach, we can easily test various cores. We can add custom instructions. We can combine different features and options without any changes on the test bench itself. So we have just one test bench and several dozens of core variations running in the CI. And just by the way, we are getting an ISS model which exactly matches the implementation of the DUT, which is important because ISS is also part of our IP delivery. So this approach is not limited to TGC family. It is designed for TGC family, but we can use the same approach also to test other cores, although some adaptations of the test bench would be required. This is it from my side. Thank you very much.
Thank you, Stanislav. I thought that was really compelling and interesting. We do have a couple minutes for questions. Do you have a question? There's one here.
Thank you for the presentation, on which you focused on functional core verification. I was wondering if you could say anything about your strategies for performance verification and also non-core components, like let's say caches, or for example.
Actually, we're just starting the implementation of caches and the verification of caches. For performance, we use another test bench where we can execute several benchmarks. We also use an approach from the University of Darmstadt to run different benchmarks where we can compare, in the same environment, we can compare our results with the results of other cores. But then the important thing is that the environment is exactly the same.
Okay, do we have another question? I have a question. It looked like from your VIF interface, especially on the instructions side, did the instructions executed by the model in this setup depend on the PC of the processor, or were you bypassing the instruction fetch to inject instructions directly?
No, the instruction will be the instructions will be fetched. Just yeah, you're starting your core. It has its program counter. The program counter runs, and it fetches the instruction, and the test bench ensures that correct instruction will be fetched.
Okay,
Yeah,
so if you generate a random instruction stream, but you have a branch somewhere, will some of the instructions never be executed?
No, if we have a branch, then the branch will be taken, and the instruction, I mean, this is an endless stream of random instructions. So the next instruction will not be executed, but then it will be generated at some other point in time, and then it will be executed, right?
Okay.
Yeah.
Okay, we can talk more later. Okay,
Yeah.
let's thank Stanislaw one more time.
Thank you.
Thank you.